Welcome back, chemistry students, to Unit 3, Intermolecular Forces and Properties. Today we will be talking about Unit 3.2, Gas Laws. So because gases have no intermolecular forces, gases can be a little challenging to understand, but when it comes to a gas, we can describe gases by one of four of its qualities, right? How much gas you have, how much space that gas occupies, how fast its molecules are moving or its temperature, and the pressure a gas exerts. Now, pressure is something you might not be very familiar with. So to start you getting familiar with pressure, in class I demonstrated crushing a soda can or a 50-gallon drum or an oil tanker. Now, the way that works is that I heated up an empty soda can. That empty soda can, the air inside, as it got heated, moved faster and faster, and therefore would exit the can. There was less air in the can than outside of it. And when I flip it upside down, creating a seal in a water bath, those molecules of gas slow down to the point that they exert a lower pressure. Because pressure is just the collisions of molecules with the container they're in. It's a force for a specific area. So if you are standing at sea level and you put your hands out to either side of your body, there's 14 pounds of air pushing down on you at any given moment. That 14 pounds of air is all of Earth's atmosphere pushing down on you. And that is more than sufficient to crush a soda can or a 50-gallon drum or even an oil tanker, because that is a colossal amount of matter colliding with you. You have just grown used to it, so you don't normally recognize that amount of collisions. Now, pressure is something we've known about for a long time. Angelista Torricelli represented this by creating what's known as a barometer. A barometer is a tube of mercury flipped upside down into a bowl. The air around you, that 14 pounds of air, is enough to push on the mercury to hold it in a graduated cylinder. Torricelli showed that at sea level, the air around you is enough to hold the mercury at 760 millimeters. So Torricelli said at sea level, you're experiencing 760 millimeters of mercury. This experiment was used in so much, from engineering to physics to, yes, chemistry, that a millimeter of mercury was renamed a torr in Torricelli's honor. And those are our first two units of pressure. If you are at sea level, you're experiencing 760 millimeters of mercury or 760 torr. They're synonymous, and unfortunately for you, you do have to know both. Now, Torricelli's barometer we still use today, right, to measure barometric pressure. You have heard of the pressure. You have been watching the news. You have seen weather reports where they talk about barometric pressure. That's where this comes from. Now, Torricelli's experiments were used widely throughout the world, specifically because they created something new. Torricelli's experiments came about towards the end of the Renaissance, when it was believed that all things were made up of something, right? Even fire they had an element for, and when a fire went out, it was because you ran out of that element. They didn't understand that there's such a thing as an absence of material. So when Torricelli flipped his graduated cylinder upside down and this absence of matter occurred, this vacuum happened. The word vacuum had never been identified. How can you have not something? It was effectively like chemists had learned about the number zero. What is that concept? What is the absence of something? One scientist in particular, Pascal, was obsessed with this idea of a vacuum, and he replicated Torricelli's barometer over and over again. He decided to perform his own experiments. Being French, he used the work of Newton and described the pressure exerted on something as a force, newtons, per some area, square meters. So 1 Newton for every square meter was later defined as a Pascal in his honor. Now, 1 Newton for every square meter is very small. It's about the same as a dollar bill resting on your hand. Since a Pascal is so small, Pascal's experiments showed that if you are at sea level, you are experiencing 101,300 pascals, which is an obscene number of decimal places. So we change this with the metric system by saying if you're at sea level, you're experiencing 101.3 kilopascals. So now we have 3 units to describe one idea, the amount of collisions with the walls of a container. If you are at sea level, you're experiencing 760 millimeters of mercury, 760 torr, or 101.3 kilopascals. Since there were 3 different units, scientists would have a hard time understanding people's research papers. If someone was writing a research paper in Italy, they would use torr. If they were French, they would use kilopascals. The English specifically would use millimeters of mercury. This led to a lot of infighting in the scientific community. When you read a paper about a gas property, was it written in millimeters of mercury? Was it written in torr? Is 100 a lot of pressure? Is 100 a little bit of pressure? That was the problem. So in the 50s, a conference was convened of all physical scientists to come up with a universal idea for pressure, one unifying pressure unit. So they agreed that the pressure at sea level in France, where the conference was held, would be called 1 atmosphere. And you can think of it kind of like the gravity on Earth, right? Like if you are on Earth, you experience 1 G, 1 gravity of Earth. If you go to the moon, you experience 1/3 of the gravity because the moon is 1/3 of the mass. If you go to Jupiter, you experience 6 gravities because Jupiter exerts 6 times the gravity on matter. So 1 atmosphere is effectively 1 Earth's worth of pressure pushing down on you. So we now actually have 4 units of pressure that unfortunately you need to be able to manipulate and change and be comfortable with. You don't have to have them memorized like you do in first year chem. They are on your formula sheet. It gives you that 1 atmosphere is the same as 760 millimeters of mercury and 760 torr. The only one it doesn't give you is kilopascals, but it's probably important that you know. So let's get some practice at this, converting from 1 unit to another. And again, we're just going to use our factor label method to cancel out units. At the bottom of the Marianas Trench, which the pressure is 1,600 pounds for every square inch. That's because you have an entire planet worth of atmosphere pushing down on you, but then you have an entire ocean. So if I want to know how many atmospheres this is, I can do that conversion. 16 pounds per square inch is 1.1 times 10 to the 5th kilopascals, just taken from the problem. If I want to know how many atmospheres that is, I can set up my factor label method so that my factors cancel out. So I can use the conversion here, putting kilopascals on bottom so that they cancel out and converting to atmospheres. For every 1 atmosphere, there's 101.3 kilopascals. If I multiply by that factor, I'll end up with my answer, which is 1,086 atmospheres. So you can think of it as there are 1,000 Earths worth of air pushing down on you at the bottom of the Marianas Trench. That's why if you take a styrofoam cup from sea level down to the bottom of the Marianas Trench, it gets crushed down to about the size of a thimble, because styrofoam is just mostly gas, and as you push on that gas, it gets smaller. Let's do another one. Outside of an airplane, the cruising altitude of 30,000 feet, the pressure is 226 millimeters of mercury. What is this in torr? 226 millimeters of mercury. We can convert to torr using our conversion factor. Now, you're smart, you're pretty, gosh darn it, people like you might realize that these are synonymous, but if I wanted to show the work for it, for every 760 torr, there are 760 millimeters of mercury. Millimeters of mercury will cancel out, and really it's 760 divided by 760, so it's the same. 226 torr. But if we want this in pascals, that's going to be a little bit more work. So to go from millimeters of mercury to pascals, I don't really have a straight conversion. I do have kilopascals, and I can convert from kilo down to the base unit of pascals. So if I have 226 millimeters of mercury, I can convert to kilopascals using the conversion factor, where millimeters of mercury cancels out, leaving me with pascals. For every 760 millimeters of mercury, there are 101.3 kilopascals. Now, my answer there would give me kilopascals, but I don't want kilopascals, I want pascals. For every 1 kilo, there are 1,000 base units. So again, if I multiply by all my conversion factors, I'll come up with an answer, which is 30,123 pascals, which sounds like a lot, but is really not that much, considering that you are at 101,000 pascals. 30,000 is very small. There's a lot less air pushing on you at that altitude. There's less air around you. So in your packet, you'll find some practice on conversions on page 19. Pause the video and do page 19 using the conversion factors. Again, they are on your formula sheet. The only one that's not there is that 1 atmosphere is 101.3 kilopascals. Now, this air pushing down on you can literally compress matter. You can take a gas and force it together. As you force it together, those intermolecular forces will build up and it will turn into a liquid. When you can push on a liquid to the point that the intermolecular forces get stuck and you end up with a solid. So if you release pressure, the opposite has to be true. If I take pressure off of something, that's going to weaken those intermolecular forces. Some things have a very high vapor pressure. Vapor pressure is the concept that a molecule on the surface is held in place by its attraction for the molecules beneath it. Molecules on the surface have much less attraction than molecules on the interior of a substance. So the molecules on the surface can get hit by sunlight or just ambient radiation and turn into a gas. Now that gas will exert a pressure on the surface of the liquid. That is its vapor pressure. When you heat something up, the vapor pressure increases because you have more and more molecules escaping into a gas. Ultimately, a substance will boil when the vapor pressure is greater than the atmospheric pressure, when the number of gas molecules escaping is greater than the force keeping them in place. So substances boil when their vapor pressure exceeds atmospheric pressure. So a vapor pressure diagram can be used to determine what temperature something boils. Here we have 3 substances, ether, water, and mercury. We can make a lot of assumptions about these substances based solely on this graph. On this graph, at some point, you would reach the atmospheric pressure, so 760 millimeters of mercury. Meaning, when each of these substances passes that line, that's when that substance boils. So ether would boil at this lower temperature, while mercury boils at a much higher temperature. So ether has the lowest boiling point, and since mercury has the highest boiling point, it must have the strongest intermolecular forces holding that in that state of matter. So you can use vapor pressure diagrams to talk about boiling points, to talk about intermolecular forces. These are great diagrams for easy questions. The pressure of a gas functions the same no matter what gas you have. Now, ether and mercury have different vapor pressures, but once they are a vapor, once they are a gas, they will behave the same way. They'll have no interactions between their molecules. They'll move in constant straight lines, so they will collide with the walls of the container. When they collide with the walls of the container, they'll bounce off with elastic collisions. Gases and their pressure behave independent of the gas. And one of the people who pioneered this idea was John Dalton, the same person who came up with that atomic theory that you learned about in Unit 1. He also looked at gases. Now, Dalton noticed that if I have a collection of gases, each gas in that collection contributes to the pressure. So each gas has a partial pressure. If you were to know the partial pressure of two gases, and when you combine them together in a equal size flask, the pressures are additive. So if I have gas A with a pressure of 10 and gas B with a pressure of 5, and I put them in a container the same size, that means the pressure would just add up. 10 plus 5 is 15. This is Dalton's law. The sum of the partial pressures is the total pressure. So in example 3a, that's what we talk about. We have three gases with a total pressure of 10. If the partial pressure of A is 5 and the partial pressure of B is 3, what is the partial pressure of C? Dalton's law is that the total pressure is equal to the sum of the partial pressures. So if the total pressure is 10 and the partial pressure of A is 5 and the partial pressure of B is 3, this question wants to know what is the partial pressure of C. In which case, it's just a matter of simple addition. So the partial pressure of C has to be 1.6. Dalton's law can be expanded on, though. If I have the total pressure and I know what portion of a gas, what the percentage of a gas is in that mixture, I can take that percentage and multiply by the total to end up with the partial pressure of the gas. So the air you're breathing is 16% oxygen. What is the partial pressure of oxygen in torr at standard conditions? Standard conditions meaning that you're at 1 atmosphere and it's 0 degrees outside, also known as standard temperature and pressure. So the partial pressure of oxygen would be if we took the total pressure around us and multiplied by the percent that is oxygen. So the total pressure around us is 1 atmosphere, but this question specifically asks about torr. So 1 atmosphere is not going to work. If you look at your formula sheet, you see that 1 atmosphere is the same as 760 torr. So 760 torr is our total pressure. The percent is 16%. Now you remember from algebra that 16% is not a number, it's a fraction, 16 for each 100. So the partial pressure of oxygen would be 760 times 16%, which is 121.6 torr. Now 3b gave us the percentage, that is oxygen. You'll notice though, the formula in your notes has the moles of a particular gas over the total number of moles, known as the mole fraction. Mole fraction is simply to take the moles divided by a total number of moles. It would work the same as a percentage, so that's why I was able to use percentage here, because a percentage, you could just assume you have 100 moles, so 16% would be 16 moles for every 100 moles. But either way, you would end up with the same answer. So when you practice this on page 20 for number 2, notice there's not a percentage there, but it does tell you the mole components that go into the mixture of gas. So you will use those mole components as your percentage, as it were. Use your mole fraction. Please pause the video and do page 20. When we describe gases, we can describe them in terms of their pressure, how much gas there is, the volume that gas occupies, and how quickly it's moving. So these next series of laws are how these principles interact with each other, because they will behave or change depending on how each works. The first is the easiest to understand. If you've ever held an empty 2-liter bottle in your hand with the cap on, when you push on that empty 2-liter bottle, it lets you collapse it. It's up to a point. Eventually, it will start pushing back. That's because volume and pressure are inversely proportional, meaning when you put pressure on a gas, it will collapse its volume. So as pressure goes up, volume goes down. Or if you release the pressure on a gas, if you expand a gas out, its volume increases, the pressure decreases. Because if there's bigger space, there's less collisions occurring. Now, the person who looked into this was Robert Boyles. Robert Boyles mathematically showed that if you take the pressure of a gas at standard temperature and multiply it by its volume, you always end up with a constant. And since it is a constant, if you were to change the pressure to something new, the volume would have to change to match that new pressure. So we could actually set the pressure and volume of our new system equal to the pressure and volume of our original system. So pressure times volume equals pressure times volume. This is known as Boyle's law. So if I have a balloon filled at standard temperature and pressure, STP. STP is an abbreviation for a set of conditions. Standard temperature is 0 degrees Celsius and standard pressure is 1 atmosphere. It assumes everyone on Earth can find an ocean when it is snowing. That's how you can conduct gas experiments. So we standardized it. So standard temperature and pressure, 1 atmosphere and 0 degrees Celsius. A balloon is filled with 50 liters of nitrogen gas. At an altitude of 30,000 feet, the pressure in the balloon drops to 226 millimeters of mercury. What is the new volume of the balloon if temperature remains constant? So I have a volume that I start with, and the question asks about a volume that I end with. It gives me a new pressure, and I have a starting pressure. Now, one of the things of note here is that my two pressure units are different. One standard temperature and pressure is 0 degrees Celsius in 1 atmosphere, but you're smart, you're pretty, gosh darn people like you, you know that 1 atmosphere can be represented a number of ways. And one of them is to represent it as millimeters of mercury. So 0 degrees Celsius and 760 millimeters of mercury is standard temperature and pressure as well. So Boyle's law is that the pressure and volume have to remain the same. So pressure times volume has to equal the pressure times the volume. So if I want volume 2 by itself, I can divide by pressure 2 on both sides, and I would get that the pressure times the volume of what I started with divided by the pressure that I end with has to equal the volume that I end with. So the pressure that I started with was 760 millimeters of mercury. The volume I started with was 50 liters, and I end with a pressure of 226 millimeters of mercury. The millimeters of mercury cancel each other out, so my answer has to be in liters, giving me 168 liters as my new volume. And that makes sense. At a lower pressure, there's less pushing down on that gas, so the gas will spread out and take up more space, so the volume increases. All right, a balloon is filled to 500 milliliters with 1 atmosphere of air. When placed in a vacuum, the volume increases to 1,000 milliliters. What is the pressure in the vacuum? So I have a volume that I'm starting with and a pressure that I'm starting with, and it asks about the new pressure when the volume changes. So again, Boyle's law is that the volume and pressure has to equal the changed volume and pressure when multiplied together. So if I want pressure 2 by itself, I would divide by volume 2 on both sides. So I get that the pressure times the volume of what I started with divided by the volume I end with has to equal the pressure I end with. So the volume I started with was 500 milliliters. My initial pressure was 1 atmosphere, and I end up with a volume of 1,000 milliliters. Milliliters will cancel out, and my answer is going to be in atmospheres. 500 times 1 is 500 divided by 1,000 is a half. The pressure dropped to a half an atmosphere. You can practice this on page 20. Pause the video and do page 20 in your packet. Another way to describe a gas is in terms of its temperature. If you change the temperature of a gas, its volume will change accordingly as well. You can view this when you see, you can see this if you put a peep in the microwave. Peeps are made of marshmallows, and so they're mostly gases. And when you microwave your peep, those gas molecules move faster and faster, and it grows and gets really big. Now, the movement of particles is what we're really seeing here. And remember, when it comes to temperature, the best representation of a movement of particles of a gas are the temperatures in Kelvin. So anytime we do these gas laws, your temperatures must be in Kelvin in order to do them. So remember, it's degrees C plus 273. Charles was the inventor that looked at this, and he saw that if you take the volume and divide by the temperature, you always got some constant. So if I have a new volume, the constant remains the same, so the temperature has to change as well. So volume divided by temperature always equals the volume divided by the temperature of a gas. So we can practice this. A gas balloon is filled at a volume of 3 liters. So I've got a volume to start with at standard temperature and pressure, which again is 1 atmosphere and 0 degrees Celsius. Remember though that temperature for gas laws has to be in Kelvin, so that's not 0 degrees Celsius, that's 273 plus 0, or 273 Kelvin. If the pressure remains constant but the balloon is heated to 25 degrees Celsius, what is the new volume of the balloon? 25 degrees Celsius, remember we can't work in Celsius, it needs to be in Kelvin, so we'll add 273, so 25 degrees Celsius is 298 Kelvin. Volume divided by temperature will equal the volume divided by temperature. If I want volume 2 by itself, I would multiply by T2 on both sides so that it cancels out. So my new volume is going to be my new temperature times my original volume divided by my original temperature. So my original volume of 3 liters divided by my original temperature of 273 Kelvin times my new temperature of 298 Kelvin. Kelvins cancel out. My answer is going to be in liters. So it comes out to be 3.83 liters is my new volume, which makes sense. I've heated it up, so my volume should increase. When a balloon is inflated at 1 atmosphere and with 300 milliliters of air at 27 degrees Celsius is dropped into a pool of liquid nitrogen, the volume drops to 78 milliliters. What is the temperature of the liquid nitrogen in degrees Celsius? So I've got a volume that I start at and a temperature that I start at. However, that temperature is in degrees Celsius, so we need to add 273. 27 plus 273 is 300 Kelvin. It's dropped into a pool of liquid nitrogen and the volume drops to 77 milliliters. What is the temperature? So we're looking for temperature 2 in this case. If I want T2 by itself, I can multiply by T2 on both sides to cancel it out, giving me T2 times V1 over T1 equals V2. And now if I divide by this fraction V1 over T1, I'll end up with that T2 equals V2 times T1 over V1. So V2 is 76.9 milliliters. T1 is 300 Kelvin. V1 was 300 milliliters. Well, coincidentally, that's pretty straightforward. 300 divided by 300, milliliters divided by milliliters, tells me that T2 is 76.9 Kelvin. Now that's a great answer. However, the question wanted to know what it is in degrees Celsius. So in order to do that, we'll subtract 273 from 76. 76.9 minus 273 is a negative 196.1 degrees Celsius. With that, you are able to do page 20. Remember that at all times, your temperature must be in Kelvin. So remember, it's degrees C plus 273. Go ahead and pause the video and complete page 20 in your packet. Finally, pressure and temperature are related. If I heat up a gas, that gas will collide with the walls of its container more often and pressure will increase. Gay-Lussac is the scientist that mathematically showed that the pressure divided by the temperature in Kelvin will always produce a constant. You aren't really responsible for knowing Gay-Lussac's law, but you are responsible for combining it together with the other two gas laws to form the combined gas law. The combined gas law uses Boyle's law, pressure times volume always equaling some constant, and Charles' law, volume divided by temperature always equaling some constant, and Gay-Lussac's law that pressure divided by temperature will always equal some constant. So the combined gas law is pressure times volume divided by temperature will always equal a new pressure times a new volume divided by a new temperature. Now personally, I do not memorize it in this fraction form, I cross multiply. In other words, I switch my t's. Giving me PVT equals PVT 112,221, and that way it's all in one straight line. So when we do example 6, I'll be using this formula. A toy balloon has an internal pressure of 1 atmosphere, so I've got an initial pressure and a volume of 5 liters. If the temperature where the balloon is released is 20 degrees Celsius, so I have a temperature to start with, but remember, we can't work in degrees Celsius, so 273 plus 20 is 293. What will happen when the balloon is raised to an altitude where the pressure is 0.6 atmospheres and the temperature is negative 15 degrees? Remember again, negative 15 degrees we can't work with. So 273 minus 15 is 258. So PVT equals PVT 112,221. If I want V2 by itself, I can divide by P2 and T1 on both sides, giving me that V2 would be T2 over P2, T1, V1, P1. And that's just a matter of plug and chug. P1 was 1.05 atmospheres, V1 was 5 liters, T2 was 258 Kelvin, P2 was 0.6 atmospheres, and T1 was 293 Kelvin. Kelvins are going to cancel out, atmospheres are going to cancel out, leaving me with liters. So my answer here is in liters, and once we get it all multiplied out, we come up with a volume of 7.11 liters. You can get lots of practice with the combined gas law by doing page 20 in your packet. Lastly, the relationship between pressure and the amount of gas you have is known as Avogadro's hypothesis, that if you have 5 balloons all at the same pressure and the same volume, they all contain the same amount of gas. Because the molar volume of any gas at standard temperature and pressure, 1 atmosphere and 0 degrees Celsius, is 22.4 liters. It does not matter what the gas is, all gases have the same molar volume. So if we wanted to, you could say the pressure divided by the number of moles of gas would equal some constant. Now, in all of our explanations here, we have always said there's some constant, and I've used the variable r. That's not a mistake, and that's not just some random letter I chose. There is an ideal gas constant given the variable r. Now, that constant is taking all of the gas laws we have looked at so far, whether you're taking Boyle's law, or Charles' law, or Gay-Lussac's, and then throwing in Avogadro's hypothesis. The ideal gas law is that you can determine any of the 4 ways to describe a gas by using the formula PV equals nRT. In fact, this gas law is the one that's on your formula sheet. On the back of your periodic table, your formula sheet has the gas law. The ideal gas law summarizes all the ones we've just talked about. PV equals nRT. Since the ideal gas law contains a constant R, if you were to rearrange this, PV over NT equals that constant. Since it is a constant, if the pressure, volume, or temperature changes, they have to equal one another. So while the combined gas law is not written for you on your formula sheet like Dalton's law is, the ideal gas law does allow you to find it. But the ideal gas law is probably the most important gas law of the lot because it contains all four of the variables by which we describe a gas. We can describe a gas in how much space it takes up, its volume, what temperature its particles are at, their kinetic energy, so Kelvin temperature, how many moles you have, or their pressure. Now when it comes to pressure, remember pressure has four different units. We could describe pressure in atmospheres, or millimeters of mercury, or torr, or kilopascals. So depending upon what unit of pressure you use will change the value of R, depending upon that unit of pressure. If you're in atmospheres, you use 0.08206. If you are in torr or millimeters of mercury, you use 62.4. And you don't have to have those memorized. They are right here on your formula sheet. We are talking about the ideal gas law, which has pressure, volume, number of moles, and temperature. So you need one of the R values that has volume, pressure, moles, and temperature. Do not use this first value because we aren't talking about energy. So having joules in a unit is going to throw you off. So your ideal gas constants are right here. So with that being said, let's do some practice. How many moles of gas does it take to occupy 120 liters at a pressure of 2 atmospheres and a temperature of 340 Kelvin? So again, PV equals nRT. This wants to know about your moles of gas. So we're solving for N. We have a volume, a pressure, and a temperature. So if I want N by itself, I'll divide by RT on both sides. I get PV over RT equals N. So my pressure of 2.3, my volume of 120, my temperature of 340, and then we have to say R. Which R value do we use? Well, our pressure is in atmospheres, so we need the R value that has atmospheres in it. So I'm going to use 0.08206 liter atmospheres for every Kelvin mole. That way Kelvin cancels out, and when we divide by a fraction, atmospheres and liters cancel out. So we find that you have 9.89 moles of a gas. If a 50 milliliter container holds 0.45 moles of gas at a temperature of negative 15 degrees Celsius, what is the pressure in the container? So PV equals nRT. If I want P by itself, I divide by V on both sides, giving me P equals nRT over V. Now N's pretty straightforward, 0.45 moles. T is not, however. We'll come back to R, but for right now, let's talk about temperature. Our temperature value in this problem is not very straightforward. It's negative 15 degrees Celsius. Remember, when working with a gas, you must be in Kelvin, so we're going to add 273 to a negative 15 for a temperature of 258. Our volume is also not particularly straightforward. In order to make these R values work, we need liters. So milliliters can't go into this equation. So in order to do that, we'll take 50 milliliters and change from milliliters to liters. For every 1 liter, there are 1,000 milliliters. So 50 milliliters is 0.05 liters. Now, R changes with the unit of pressure. Since this problem did not ask for a specific pressure, we actually could use any 3 values of R and get 4 different answers. Remember that millimeters of mercury is the same as torr. So if we wanted an answer in atmospheres, we would use 0.08206 and get 191 atmospheres. Or if we used 62.4, we would get 145,000 torr, or millimeters of mercury. Or if we used kilopascals, we would end up with 19,300 kilopascals. All 4 of these answers are correct because all 4 are the same value. It's just a matter of which R value we use. One of the practical uses of the ideal gas law is to determine the molar mass of an unknown gas. Since we can substitute the value of N, the number of moles would be if you took the mass of a gas and divided by its molar mass. That's what this formula is showing here. So if we replace N with the mass of the gas divided by its molar mass, we could solve for molar mass. Divide by PV on both sides. The molar mass of a gas would be the mass times the ideal gas constant times temperature times pressure divided by volume. Mass divided by volume is the same as density. So the molar mass of a gas is equal to the density of a gas times the ideal gas constant times temperature divided by pressure. Personally, I remember this as the kitty cat formula, the meow meow kitty cats, because cats go meow meow, like molar mass, meow meow. And cats cover their pee with dirt. Now, this formula is not on your formula sheet, at least not in so few letters, so it's one of these things that's easiest to memorize. Remember it as cats cover their pee with dirt, meow meow kitty cat. Cover their pee with dirt. So we can use the density of a gas to determine its molar mass if we know its pressure and temperature. So we have a gas that's produced that has a mass of 1.2 grams and occupies 677 milliliters. The temperature in the lab is 23 degrees Celsius and the pressure is 1 atmosphere. Calculate the molar mass of the gas and determine its formula. We can use our molar mass kitty cat formula to determine the molar mass. We just need the density, the temperature, and the pressure. Now, the pressure is pretty straightforward, and the temperature is relatively straightforward. Remember, we can't work in degrees Celsius, so we'll add 273 to 23 to get a temperature of 296 Kelvin. So with those two out of the way, the only thing missing is our density. Which, remember, density is simply mass divided by volume. So mass is 1.211 grams. Our density needs to cancel out the liters in our ideal gas constant. So we need to use our density in grams for each liter. So if I have 677 milliliters, that's 0.67 liters for a density of 1.79 grams for each liter. So the ideal gas constant we use, since our pressure is in atmospheres, is 0.08206. Our temperature was 296 Kelvin, and our pressure was 0.987 atmospheres. all said and done, we get 44 grams for every mole as our molar mass. So to determine the identity of the gas, with a molar mass of 44, it's nitrogen and oxygen base. Nitrogen monoxide would give you a molar mass of 30 grams for each mole. Nitrogen dioxide would give you a molar mass of 46 grams for each mole. So what if we had nitrogen monoxide plus another nitrogen, so dinitrogen monoxide, would give you a molar mass of 44 grams for every mole. That must be our gas, dinitrogen monoxide. And with that being said, we are done with Unit 3.2. You can go ahead and do page 20 through 22 in your packet, practicing the ideal gas law, solving for molar mass. Additionally, make sure that you do your AP classroom homework, and I will see you next time when we talk about solutions.